software engineering for computational science kind of person. And this is something that is not given enough importance in most of the scientific endeavors, and eventually people suffer enough for it that they start looking for solutions sometimes too late, and the whole process becomes more complicated. So I think it's useful to understand that a certain amount of thought given to software engineering of your code, especially if you have any idea of doing multi-physics simulations, is extremely important. Secondly, if you are delving into the world of HPC, what you will find is the shelf life of the machines is very small, and the machines change considerably from one generation to another. And if anything, that pace of change is accelerating. So, you know, what used to be that scientific computing that was a heroic developer who was going to spend a weekend developing code, forgetting all about sleep, fixing everything that goes on in their codes, and eventually getting it to run, has pretty much played out. There are still some problems you can get to that way, but not very many. And what's of more interest these days is efforts that require much more orchestration than this model did. So, you know, the most interesting questions that could be answered can no longer be done with that kind of heroic effort. And the languages that were supposed to have delivered the abstraction whereby you could program much more rapidly and forget the details of housekeeping, infrastructure management, I/O, etc., still haven't delivered. We are somewhere in this land where neither option works very well, and so there is no choice but to look seriously at software process, the division of responsibilities, the actual design of your software, etc. And any group of people working together is a lost cause unless there is a software process involved. So what are the components that you should be aware of in the software process? The first one, without which you can't even begin to start doing a software process, is the code repository, because you want to be able to sync what other people are doing. You want to be able to get their stuff seamlessly into your working directory, and you want to be able to use it without having to explicitly maintain different versions, and it can get very confusing very fast. And I can tell you that even when you're working with a code repository, if you have multiple projects going, it becomes really hairy keeping track of what all is going on. And I will give you an example, specific example from Flash days for that. You have to worry about a build process, because chances are you will have multiple files, and each system will have its own idiosyncrasies that you have to cater to. So you should have a build process. You should have a code architecture, coding standards, verification process, maintenance practices. And if you happen to have a publicly distributed code, you have to think about how you want to distribute, how far you want to distribute, what do you want to allow your users to be able to do to the code, how much are you going to allow the modification and redistribution of the code, and how are you going to attribute the IP contributed by other users, etc., etc. And I will go through each one of them one by one, where I would try to give a general flavor for what happens in the community, and then I will give specific examples, and most of those examples will come from Flash, because that's what I'm most familiar with, right? So code repositories, they come in two flavors. There are the centralized version control, and that's where actually version control started basically with CVS. And you know, all those of us who are old enough to have started with CVS can still remember all of the frustrations that went with CVS. For example, if you had a directory in CVS, it lived in perpetuity. You could never get rid of it. So then roughly about 12 years ago, SVN or Subversion came along, and that was revolutionary because it allowed you to do so many things that CVS wouldn't. And so many people, and actually you will find that most of the mature code bases are still working with Subversion. But more recently, the more popular options are the distributed version controls, of which the most popular are Git and Mercurial. So in centralized version control, the synchronization happens to the central place where the repository is located, whereas the distributed version control, your synchronization happens through exchange of patches. And one can maintain multiple local branches. So the advantages versus disadvantages. In Subversion, if you typically how you work is you get your working copy, you make modifications to your working copy, you check in. Now, if you want to have much more extensive modifications that might collide with others, you typically have to create your branch and you have to check into it, and then you have to merge the branches. Whereas with Git and other distributed versions, what happens is you basically work within a local copy of the repository. Your check-ins are local check-ins. They're not colliding with people until you do this explicit synchronization step. So it allows for more flexibility, but it also then requires, if there are multiple people working in that project, it requires greater discipline for the purposes of keeping the various branches basically synchronized with one another. And the other problem that happens with distributed version controls, and that needs to be addressed right up front, is that gatekeeping for the code base becomes a little bit more challenging, requires more discipline from people. So I'm not going to go into the details of the distributed version controls very much. Yeah. If somebody, for example, goes off and keeps on doing development without synchronization and then wants to do a merge, you can have a collision that can be really, really bad. And also, for example, you will not see, so if you have a centralized repository and people are making changes, you can see them immediately. People are checking and you can see them immediately, and you can act upon them if you have designated a gatekeeper in your development effort. In distributed versions, it can go on for a very long time before anybody sees what you've been doing. And therefore, what you ultimately bring into the code base can become much harder to monitor. So the one that I'm going to go in some details of is Subversion, because at present that happens to be the most frequently used code repository in major software projects. So it is a central repository system, and there is one master version of the state of the code. So users, what you do is you get access to a SVN, you check out a working copy of the master repository. Now, the repository can be accessed via an RSH connection, an SSH connection, an SVN, or an SVN server. Most often, it is an SSH connection because you want to have the secure socket layer underneath. All of the user interaction is considered a client-side operation, and the protocol operates in a transactional mode, which means that a user that is doing a check-in gets a lock on the system until the check-in is complete, so that the two different check-ins do not collide with one another. When you're working with your repositories, the first thing you do is a checkout, and that's when you get a new working copy of the directory. Once you have checked out a working copy, if you just want to get incremental changes that are going on in your directory, you run an update. You also can do merging, or you can run concurrent, you can do the merge also with the update process. There is a diff which tells you the difference that is between the central, the way your working copy differs from the central repository comes through with the diff command. The add command is for adding a new file or a new directory. The delete command is when you want to, actually that ought to be remove, but maybe delete works also. If delete doesn't work, it's remove. For deleting a directory or a file from the repository. And then you have the way of creating branches and merge. Now the command commit, this particular command commit is where the changes that you made to your working copy get pushed onto the central repository. And at the time of commit, the SVN system does a few checks. It checks to see if your working copy is up to date with all of the files that you're trying to commit. If it's not, it won't let you commit. It'll tell you that your files are out of date, and then you run an update. Sometimes what will happen is when you run an update, you will find that you had a conflict because somebody else was working on the same file. And at that time, SVN gives you an option of resolving your conflicts in many different ways. You can either postpone it, in which case it does merges the two files and it flags the areas where you have a conflict. You can say you want to overwrite their modifications completely, in which case whatever work somebody else has done, you're basically overwriting. Now keep in mind that the repositories keep complete history, which means that even if you overwrite, you're not really losing all of that information, because you can revert back a version and you can recover that information. However, still, overwriting other people's work with your work is not always a great idea. So as much as possible, you should do a postpone and do a merge and look through the code to see what is stored in the central repository. Because if you think about it, you have a large code base and you're trying to keep, and the repository is keeping a comprehensive information about all changes, all versions that happen. You can arbitrarily go back as many versions as you want, and you get the exact same content of that version when you do that update. So the storage has to be intelligent. It cannot be storing everything, because the size of the repository will become huge. So it capitalizes on the fact that differences between versions are relatively small, and what it stores, what the central repository stores, is the difference between the two versions. And that is why if you, for example, run an update several versions over, it takes longer than if you're running an update for one or two versions, because what is happening is, as you run an update, all the changes in the intermediate versions are applied before you get the final copy of the file. And you can see there are tools that translate the history and logs into a web-readable information. And here is an example from Flash. So this is a view of the Flash repository. This is the index of the trunk. And if I go to source, I can see that these are the various subdirectories within the source, the driver, grid, etc. This column is telling you that the last time any check-in happened in that particular subdirectory was this particular revision, the time that that check-in was made, who was the author. For example, in grid, the last check-in happened on revision 20,242. Oh, good God. What's the current revision on? Right, 2,484. That happened 5 weeks ago. It was done by Klaus. We can go further deep into the subdirectory, and we can track the history of every single one of these files. This is the one we are tracking right now in grid particles. The change was done by Klaus, and it's like it's here. Notice that I'm going deeper and deeper into the change that was committed by Klaus 5 weeks ago, because I'm trying to track exactly where he made this change. There you go. So it's a previous directory somewhere. But basically, another important thing, if you look at a particular file, what you can also see is the difference from the previous version, and that is highlighted. For example, all the highlighted parts in here, this was the file, this was the instruction that was there in the original file, and this is what got replaced in that file. So you can see the difference from one version to another. If you want to see a particular version file completely, you can press view, and that will list the entire file for you. You can download it, or you can click on a particular revision, and it'll tell you which were the files that were modified under that revision. And you can see the files, every file as you click on it will display what it looked like for that particular version. Okay, so that's the example of use of, getting a web interface to see the repository. Then what else can you do with repositories? You can manage branches, which means that if for multiple people working on the same project, you can go off for a brief period of time. You can have your own branch. You can do your own check-ins without the worry of breaking the code for everybody else. The other useful things that you can do is you can tag stable branches, so you know in which version the code was working fine and was stable. You can separate the production from development, and you can also manage multiple production projects. Now also, when you're trying to do a verification and you find that something went wrong somewhere and you discovered it many versions later, you discovered it now, and you want to be, but you don't know when that error happened, what you can do is you can track back to as many versions as you want. And what you can also do is you can track back as many versions as you want in a particular subdirectory where you're trying to find out, where you're trying to track the bug that was introduced instead of the whole code base. So that makes for debugging through traceback much more easy. It also, if you're retaining enough information, it also helps in being able to reproduce the results within the limits of having the same compiler available to you to run that you ran the original version with. That doesn't always happen. So in short, those of us who've been using version control will not work without version control, because we have learned to appreciate the advantages of having version control. I manage my personal data using version control. So my CV, my list of publications, etc., everything I might manage with version control, because it just makes life so much easier. And then I want to give a specific example of unusual use for repositories. For example, in Flash, what happens is there are 4 different production campaigns that can be running. There is the type 1a supernovae, there is the core collapse supernovae that you heard about from Sean, there is the high energy density physics, and there are the fluid structure interactions. Each one of them makes use of its own, sometimes overlapping, sometimes disjoint set of capabilities that are there in the code. Each one of them wants to have their own separate production schedule. They want to be able to modify the files that they're using for their production without colliding with other projects. They want to be able to save those, but also sometimes they just want to experiment, which means they do not want all of the modifications they're making go into the permanent code repository, right? So this becomes a very difficult problem, because also the thing is that if your branches start to diverge quite a bit, it becomes very difficult reconciling various code components, and it can sometimes take, if you're not careful, days to make sure that the code compiles and runs again without breaking. We started making use of SVN in order to do this. What we said, we're not going to use trunk as the normal place where the whole central repository is kept. Instead, we've turned trunk into the area where the merges happen. So each production campaign, so there are at the moment 5 branches running, 1 for each production campaign, and 1 is the development branch. The development branch operates in the mode where normally your trunk would, which is where all of the development, all of the generic development is taking place. And then we have a stringent merge and test schedule whereby every production branch is expected to merge into the development branch once a week. And the test suite gets directed to that. So the test suite is directed to each individual production branch as needed. After the merge, whichever production branch got merged into the development branch is supposed to monitor the test suite, find all of the breakage that happened in the code, and fix it before the next production has its schedule merge. And we really have to stick to this schedule, otherwise this whole operation doesn't work. It just completely fails. And by and large, I mean, people grumbled about it in the beginning, but by and large, this system is working well because people see the advantage of it. In the end, it saves time. So that's all I was going to say about code repository. And if you have any questions about that, I'll take them now before I move on to the next step in the software process, which is build. That's a useful insight. So what he's saying is that you can also set up your ignore files, which will be ignored when you're running a commit. so that you don't inadvertently commit things that you don't really want to. So it is a useful thing to have and know about. Okay, so the build process. Why should you invest in a build process? Because when you have multiple files, individual file compilation does not scale beyond a point. And if you go to different code platforms, every platform has its own peculiarities. Every platform has, for example, if you have multiple languages, then say Fortran and C or C++, every compiler has its own preference for how it wants the name mangling to run. Some want underscore, some do not want underscore, some want double underscore, some want capitalization. And you have to know what you're doing if you want to do it by hand. Your code will depend upon libraries. If you're running on HPC platforms, at the very least, you're always going to be using MPI, if not anything else. More likely, you're going to be using MPI and some form of parallel I/O, probably some BLAS, sometimes PETC, etc., etc. And you, again, managing it all manually is not a tractable solution. So one should totally invest in a managed process, and it's usually a combination of configuration and make. You can do a configuration using autoconf or some form of scripting with Perl or Python. And then usually the best tool for make is the GNU Make for compilation, because it's a lot more flexible than your generic make is. And I have a horror story to tell about anytime when you deviate from a build process, an automated build process, and if there is time, I'll be happy to share it later on, hands-on session, a time or whatever, but it's a real horror story. Anyway. So again, and then I'll go into this, in this instance, I'll go into a specific example right away. In Flash example, the configuration is done with a Python script, which we call a setup tool. And the way the configuration works in Flash is every directory under the source tree of Flash has this file, a text file in Flash specific syntax called configuration. And this Flash specific syntax encodes information about the field variables that are going to be needed for that particular unit, the runtime parameters that are going to be needed for that particular unit, the conflicts that that unit might have with other units, what are the dependencies. For example, if you're running a Hydro, you cannot run it without a grid. So Hydro will say that I need mesh. And later on, there is an example. So it defines the configuration file, config file, defines all of these dependencies and other meta information that is needed for correct configuration of an application. Additionally, at each level, we have what is called a Makefile snippet. So this is not a complete Makefile. All you have is, if at that level in the directory you have files that do not exist elsewhere in the source tree, you add those files to be included in the object files in that Makefile snippet. And if they have any specific dependency on other files, for example, on the mod files from some files, etc., or the header files, you define those dependencies also. So this is an incomplete Makefile. So when the setup tool runs, it starts out by looking at the config file of where you're defining your application. It resolves dependencies, recursively visits all of the config files at various levels that it encounters in the process of resolving these dependencies, and it configures the Makefile by putting together these snippets of various Makefiles together. So at the end, what you have is, in one particular directory, you get a link to all of the source files that you need in order to do a successful build. You get a completely configured Makefile, and you get certain informational files that tell you all of the runtime parameters and what the default values are going to be. And all of this gets put together in one place. So after you run configuration successfully, you run a make, and that builds your file, because this is a plus equals, so it works out the dependencies much better. For example, actually, can I answer? The question is, he wants to know is, why are we just not doing an include of the make files? And I will give you the answer to that question when I'm showing you the unit hierarchy in the architecture section, because it will be much easier to follow. So please remind me when I'm giving the talk on architecture. This is an example of a Flash config file. And this config file, I don't remember where this is coming from, but a few things that are important to notice is that this is where the required units are specified, right? So it says that I need a driver, I need the stir, which is a source term unit in Flash that stirs the fluid. It needs equation of state, it needs a hydrosolver, it needs the grid, and an I/O. And then it is saying that if I/O is included, then it wants to be able to write the integrated quantities. It is saying that if the I/O is parallel, then it wants to be able to write user arrays, and also it wants to be able to read user arrays. And so these two will not be included if the I/O was running in serial mode, not in parallel mode. And again, so well, this is too much of a detail, so let's not go into it. These are the runtime parameters that are needed for this particular simulation. So, and you specify what type of the parameter it is, and you give it a default value. Now, Flash has a text file that is parsed at the time that the application starts to run, and you can replace the default values by including them in that particular text file. What else is this? Okay, and then this is a mechanism by which you can flag warnings. For example, if someone is trying to set up an application in 2D, the stir module only operates in 3D, so this is going to give a warning at the time of setup, and it's going to abandon setup. So what's not going to happen is that you configure the problem, run it, and build it, and then find out that you had done the configuration wrong, because Make is a much longer process, so it enforces the conditions that are. A simple setup will look like this, where you run it by saying that simplest is you say this is your application, whatever simulation you want to run. You do -auto. The script is smart enough to figure out all of the dependencies and take the default options and build a consistent application for you. If you want to not use the default options, then you can supply the specific options on command line when you're building the application. For example, you can say -2D. So the default build is 3D. If you said -3D here after auto, then the application would be built in 3D. Similarly, you can replace any of these default units by actually providing the path for the alternative implementation for that default unit, etc., etc. So once you have configured the problem, then you go off to GNU Make. And the purpose of the Make is to turn the source code into a library or an executable. So in a Makefile, you can only have two kinds of objects. There are no loops, there are no logical constructs, you only have variables and you have rules. So only flow control you can have is branching, which you can do with equal, if equal, or if not equal, else, and if, etc. You cannot go back to any starting point. And most of the time, what causes people trouble is the non-trivial parsing of the Makefiles, which can be very non-intuitive at times, and rules can fire and trigger in very non-obvious ways. And here is an example of what can happen, is that when you do this all and you want to echo foo, what's going to happen is the state that is at this point. It doesn't matter what came before. So for example, foo will get a value bar will get a value ugh, and when you finally run it out, when you do a make call, what you will get is this value huh. The variable in a Makefile is executed where it is used in a command, which means that it's the last instance of that variable which you will get in the command, which means that if you did, for example, definitions of the variable earlier in different ways, you may get unexpected answers. what it allows you to do is that order doesn't matter. So you can declare variables as composites of variables, you can chain them, you can extend your variables by just adding other things in top of it, so it's like a daisy chain that builds. You can also add variables on command line, and they also get incorporated into your build process. Bad points is that if you're not careful, your declarations can clobber what you specified earlier, and it's the declaration in the linear parsing is the only one that matters. So these are the recursive variables. Then there are the simply expanded variables that operate in the immediate mode only. So this has the value that is assigned at the time of where the Makefile is currently. Here there is no symbol chain is created, and this is specific to GNU Make. So for example, if you want to just append C flags equals C flags, etc., you can do it with these kinds of variables. Rules operate by saying that is pretty much operate in this way. You say a target, you say prerequisites, which is what is defining the dependencies, what you need specified. Then you have to have a tab. This tab is very important, and this is what many people starting new with Make miss, is that if you don't have the tab, the recipe doesn't get applied. And recipe is where you're telling the Make what to do in order to create that target based upon these prerequisites. Simple examples are, if you want to create the object file, then that depends upon the source, which is the CPP, and these two header files. And in order to create clobber.o, you have to make sure that these exist in the source that you're trying to compile, and then you compile it using G++, and this is the command for compiling it. If you miss this tab, your Makefile is going to come out without having done anything, and you'll be left baffled as to what happened. So because this is the trap that people can fall into, is that they start thinking of Make as a program. It is not. It is just variables and rules, and it's what is going to be generated depends upon these variable chains that are built, the builds up of rule databases, and the targets that users have specified. For example, and this you can go and practice yourself, is that if you wanted to echo trendy fashion, and you made your variable like this, and you said you've defined it as foobar as trendy and f as fashion, and you think that when you do this echo, it should come out saying trendy and fashion. But then your Makefile did not end there. There is this section in here which says if f was fashion, then if foobar became tragic, and then f became tragedy. If you run now make vars, instead of getting trendy fashion, what you will actually get is tragic comedy. So you have to pay attention to these kinds of subtleties that can happen in Makefile. Flash's example of Makefile. Each supported site has a specific Makefile.h. The variables are defined for library locations in that Makefile.h. There are variables, for example, the debug flags, the opt flags, etc., defined for compilers being used. You can use them either in optimize mode or debug mode. The Makefile snippet exploits the recursively expanded variables, and it makes sure that all the source files are defined at the level unless they are inherited. The file snippets are consolidated into a Makefile.unit for every unit. So grid has a whole directory structure, and again I'll go back to do this in much more detail when I'm showing the whole grid unit, where you can specify local dependencies. The file snippets are consolidated into a Makefile.unit for every unit, and then when the Makefile is ultimately built, the files that are included in there is the Makefile.h, which is the site specific, and Makefile.unit for every one of the units that you have included in your simulation. And with this, I am at the end of this particular section. The next is how with the architecture for the hack code. So what we decided to do is give you a flavor of two different kinds of code architectures. Hack is not a community code. It is used by a small group of people for their own research, and yet they have taken the trouble to architect it. And after Hal is finished, I'll tell you about the architecture of Flash, which has a wide user community, very many capabilities, etc., etc.